Section 9.3, the integral test and the p-series. Graph the following on your calculator using the sum and sequence commands. Which series do you think converge or diverge? Note that these series all have positive terms. So I'm going to give you a couple of minutes to do that. This right here, this is in the denominator is n to the 0.25. So I rewrote it a little neater. Right? Take a minute to try it. This one converges. Number 2 converges. Number 3 diverges. Number 4 diverges. Number 5 diverges. What do you notice about the series which converge and the series which diverge? If the exponent was greater than 1, as these two were, the series converged. If the exponent on n in the denominator was less than or equal to 1, your series diverged. And this brings us to our first series test for this section, which is the p-series. Students love the p-series because it's really just so simple. A series of the form n goes from 1 to infinity of 1 over n to the p, which would be 1 to the p, 2 to the p, 3 to the p, and so forth, is called a p-series where p is a positive constant. For p equal to 1, the series n goes from 1 to infinity of 1 over n, which is 1 plus a half plus a third, so forth, is called the harmonic series. And we have already seen that this one is going to diverge. So the p-series test says that if you have a p-series, if p, your exponent on n in the denominator, is less than or equal to 1 and greater than 0, your series diverges. And if p is greater than 1, your series will converge. Determine whether the following series converge or diverge. Notice we want to write it as our series here, and our n is raised to a power of 1, which tells me we diverge. Here is how we write it. We identify the series and what it is we know, and then we can state converge or diverge. Number 2, what we want to do with this is first of all write it with an exponent. We can see that that exponent is less than 1, so our series will diverge. This is a p-series. Identify the series. What is p, which is less than 1, so our series diverges. Okay, we know that we can write this as n to the 3/2 in the denominator, and that gives us our power to be greater than 1. So we have a p-series. P is 3/2, which is greater than 1, so our series converges. Let us recall, the smaller your denominator, the larger the fraction value is. The larger the denominator, the smaller the fraction. Compare 1/10 to 1 over 100. The larger number you have in the denominator gives a smaller value of the number. We know that 1 over 100 is clearly smaller than 1/10. The integral test. Suppose f is a continuous, positive, and decreasing function on the interval from 1 to infinity, and let a sub n equal f of n. Then the series, the sum of all my terms from 1 to infinity of a sub n, is convergent if and only if. When you see this in mathematics, IFF, that's what it means. If and only if the improper integral from 1 to infinity f of x is convergent. That arrow like that also represents if and only if, the double lines, arrows on the end. So the series is convergent if and only if the integral is convergent. And I can say it both ways. That means if the integral is convergent, then the series converges. If the series converges, then the integral converges. And our integral test says if our integral is convergent, then the series converges. And if our integral diverges, then the series is divergent. If the series converges to some number s, then our remainder, r sub n, of the actual sum that our series converges to, minus the partial sum, the sum of n terms. So our remainder after taking away a partial sum, okay, that's what our remainder is. The actual sum after taking away a partial sum, that is our remainder. So if the series converges to s, then this remainder is bounded by 0 and the integral from the nth term to infinity. So let's say I look at 5 terms. Then my s sub 5 would be the sum after 5 terms. So r of 5 would be the remainder after I've taken a sum of 5 terms. So my remainder would be bound by the integral from 5 to infinity. Note, when we use the integral test, it is not necessary to start the series of the integral at n equals 1. Also, it is not necessary that f be always decreasing. What is important is that f be ultimately decreasing. Maybe after a few terms, it then is ultimately decreasing. That is, decreasing for x larger than some number n. Maybe after 5 terms, maybe my function does this, and then it decreases. So to use this test, we must show that we have a continuous, positive, and decreasing function. That's the first thing. For this example and all of the remaining examples in this video, listen to the explanation and watch the screen while I go through the problem. At the end of each problem, you will be given time to write down everything you see. Okay, our first example. The series defined by the sum goes from 1 to infinity of n over n squared plus 1. Well, first of all, what we know is our function f of x is x over x squared plus 1. When x is positive, my function will be positive. We know our function is continuous because the denominator will never equal 0. We know our function is decreasing because, notice that, the denominator is getting bigger faster than the numerator because of that x squared. So we have a function that is continuous, positive, and decreasing. Once we have established that, we can actually apply the integral test, which means let's integrate it. Well, we know that because of our infinite bound here, we must take the limit as b goes to infinity of 1 to b. Also, this almost looks like u prime over u form. All I need to do is multiply and divide by 2. Now we're ready to anti-differentiate. Notice we have the u prime over u form, which we know is going to integrate to ln u. Notice I don't need the bars because my u is x squared plus 1, which is always positive. So I don't need bars there. So we get 1/2 the limit as b goes to infinity of natural log of b squared plus 1 minus natural log of 1 squared plus 1. This gives us 1/2 times the limit as b goes to infinity of natural log of b squared plus 1 minus natural log of 2. So let's think about what's going on here. We know that this is going to be ln 2, so that's just a constant. But as b goes to infinity, this makes my x, my independent variable, get very large, and we know that the natural log function increases without bound because its derivative is always positive. So we know that this will go off as b goes to infinity towards infinity. So it doesn't matter, once I have part of it that goes to infinity, it all goes to infinity. Now, what does this mean? If the integral diverges, the area under the curve is increasing without bound. Pause your video and take a moment to write all of this down. Okay, let's look at this series. As n goes from 1 to infinity, 1 over n squared plus 1. Let's remember, what do we have to do first? We have to show we have a continuous, positive, and decreasing function. So f of x is 1 over x squared plus 1. We know this is continuous. We know for all values of x, this function will be positive, and we know that the function will be decreasing because as x gets bigger, my fraction gets smaller. So we can state our function is positive, continuous, and decreasing. So now we're ready to use our integral tests, evaluate the integral. Well, we recognize that, of course, as arctan. Okay, so we're going to take the limit as b goes to infinity of 1 to b of 1 over x squared plus 1 dx. That is going to give us the limit as b goes to infinity of arctan of x from 1 to b, which is, the limit as b goes to infinity, arctan b minus arctan 1. We know arctan 1 is pi over 4. As b goes into infinity, arctan b goes to pi over 2. Again, when do my values of tangent approach infinite values? When our angle is pi over 2. So I have pi over 2 minus pi over 4, which is pi over 4. That is a finite value. So my series converges by the integral test because I have established a finite value. Now, important. This series does not converge to pi over 4. Pi over 4 is not the nth term. Okay, take a moment, pause the video, and write down this example. Example 6, this is our series in the sum as n goes from 1 to infinity of natural log of n over n. This is logarithmic, which increases very rapidly at first and then slows its increase down quite a bit. This is polynomial, and this is going to increase more rapidly than this after a few terms. So our series n goes from 1 to infinity of natural log of n over n. Our function is f of x equals natural log of x over x. We know natural log of 1 is 0. We know for values less than 1, greater than 0, the natural log function is negative. But for values after 1, our natural log function will be positive. However, when do we start decreasing? Well, when ln e, when x is e, I get 1 over 2.71828, and this will start decreasing when x is greater than e. Now, how do we find that out? Well, we know that the derivative will tell us when a function is increasing or decreasing. So if I take the derivative of this function using quotient rule, we get this. That denominator is always positive, so what about our numerator? Our numerator will be negative when 1 is less than natural log of x, or think about it when natural log of x is greater than 1. And so we know that natural log of e equals 1, so when x is greater than e, our function will be decreasing. Now we're ready to apply the integral test. Once again, we have an improper integral. We need to address that. What I see here is this function could be written like that, and now it's very clear that this 1 over x is the derivative of natural log of x. So we're going to let u equal natural log of x. So our du is 1 over x dx. So we are really looking at an integral of the form u du, which we can see it integrates to u squared over 2. So our integral would be the limit as b goes to infinity of u squared, natural log of x squared over 2. Now notice, natural log of x quantity squared is not the same as natural log of x squared. We know that natural log of x squared can be written and simplified like this. That is not what we have here. Okay, and I'm going to bring that 1/2 out in front. And now I have the natural log of x squared from 1 to b. Substitute b, subtract, substitute 1. We know this is 0. 0 squared is 0. So what is happening here? As b goes to infinity, natural log is going to infinity. So this goes to infinity, and we say our series diverges by the integral test. Now, once again, notice to use the integral test, you have to stipulate at the beginning if the rules apply. Our function's positive, continuous, and decreasing, and we found ultimately decreasing after x is greater than e. Pause the video and take a moment to write this down. Now we're going to move into something involving error. Approximate the sum of the convergent series, so you're being told it's convergent, and we know using the p-series test that it is, using the indicated number of terms. Include an estimate of the maximum error for your approximation. So we want the error after 6 terms. So let's list our 6 terms and find the sum. And we have to use our calculator to do that. Our sum after 6 terms is 1.0811 and a bunch more decimals, approximately. So our remainder after the sum of 6 terms goes from 6 to infinity, and we can evaluate that on the calculator and find that is approximately 0.0015. Now, what does that tell me about my actual sum of the series from 1 to infinity? If this is the sum after 6 terms, and this is the sum of all the rest of them, doesn't it make sense that our total sum would be this and this? Now, what does that tell me? Our total sum of the series. So we know our remainder, which has to be greater than or equal to 0, so not negative, after 6 terms is this. We therefore know that our series, well, we know after 6 terms it's 1.0811, so with all of the term it's certainly larger than that, but it's got to be less than or equal to this sum. Another name for remainder is error. So how far off were we from the actual sum? Okay. Notice in my inequality, what I did is took what I knew about my remainder, and I added 1.0811 because my first 6 terms added to that. So the whole series has to be somewhere between these two values. Take a moment to write this example down. Your TPs for this section, 3, 11, 29, 35. See you next time.